I recently made a video about how the megafauna like woolly mammoths and woolly rhinos and giant ground sloths went extinct at the end of the Pleistocene during this time that we call the Younger Dryas cooling event, and how this rapid Younger Dryas climate change contributed to those mass extinctions. But what caused this rapid cooling event? We have some ideas whether it was meteor impact or volcanism or some other things we'll talk about later in the video. But obviously, an extraterrestrial impact is the hypothesis that gains the most public attention. However, there's a lot of competing information out there about what we call the Younger Dryas Impact Hypothesis. So in this video, I'm going to talk about, was there an impact or not? What is our evidence for both of these cases? And what was the cause of the cooling if there wasn't? Before we jump into that though, let me give some background information so we're all on the same page with when this event occurred in time and what period this marks, all of that. So essentially, this Younger Dryas was a period of rapid cooling that went from around 12,900 to 11,700, 600-ish years ago. It followed directly after a period of warming called the Bowling asteroid warming, which happened as things started warming up after the last glacial maximum, or LGM. So what's the last glacial maximum? What does this mean? Well, just to give a little bit more background, the Pleistocene epoch, which went from about 2.6 million years ago till the end of the Younger Dryas, 11,700 years ago, this epoch is marked by interglacial cycles of the Ice Age. So essentially up and down fluctuations of temperature throughout the Ice Age, which were also associated with expanse and retreat of glaciers, depending on whether it was a cool cycle or warm cycle. We call these glacial cycles, the ones where they expand in the cooling periods, glacial cycles or glacial maxima. And then the warming spikes are called interglacial cycles, between glacial cycles, and they are marked by glacial retreat. And essentially, leading up to where we are today, the last glacial maximum is called the last glacial maximum. And so this was the last major cooling of the Ice Age that we had. And then we started coming out of it in, this expanded view over here. And as we came out of it into our current interglacial period, we had warming from coming out of the cooling time. But then we dropped right back into cooling, which we called the Younger Dryas, and then we came back to our interglacial warming. So what caused this Younger Dryas cooling? Why didn't we just continue to warm in the interglacial cycle? Why did we go from starting to warm and then drop back down to cooling and then warm again? I should also mention that these cycles that we're seeing throughout the Pleistocene Ice Age are caused by astronomical changes in Earth's orbit, wobble, and tilt that happen on a periodic basis. So that's why the cycles are very predictable in periodicity and timing. So these astronomical changes are what led us into the major, cooling maxima, warming, interglacials, back and forth. But then as we came out of our last glacial maximum into the current interglacial, the little tiny rapid cooling spike that is the Younger Dryas is not an interglacial. It's just a little bit of a dip as we warmed in our major interglacial. And so that is not caused by astronomical factors, but rather something else, which we'll explore for the rest of the video. Like I mentioned, there are multiple hypotheses for this cooling event or rapid cooling period, but one that catches public interest, and that is the YDIH, or the Younger Dryas Impact Hypothesis, proposing that an impact caused this sudden cooling. How does an impact, such as an asteroid, comet, meteor, whatever, caused cooling? Well, as I've talked about, for example, with the KPG or Cretaceous Paleogene mass extinction, the one that took out the non-avian dinosaurs, impacts cause a multitude of climate changes, one being what we call impact winter, because it throws a bunch of dust and debris and ash into the atmosphere, which leads to the blocking of sunlight. And this causes, one, major cooling, and two, the blocking of sunlight stops photosynthesis for a bit, which can be really detrimental to life, which is one of the reasons that the KPG extinction was so massive. So what is our evidence for the YDIH, or the impact at the Younger Dryas boundary, well, we do see an increased amount of iridium, or kind of iridium spike, in the rock record of some sections that mark the Younger Dryas boundary around 12.9 thousand years ago when the Younger Dryas began. And why do we care about iridium? Well, iridium is more common in extraterrestrial objects than on Earth. So when we see spikes of it, for example, we see this globally throughout Earth at the KPG boundary. When we see those things, we know that, or at least it hints at some sort of extraterrestrial source rather than Earth source. We do see some spikes of iridium in the Younger Dryas sections, or some of the layers of rock around the world that are dated to the Younger Dryas. However, it's not that consistent around the world. Likewise, we see nanodiamonds, which are tiny diamonds that form during high energy events like impacts. We also see microspherules and melt glass, which are things that also form at high temperature and pressure consistent with an impact. And we also see black mats, which are black, very dark, organic rich layers in the rock record, which potentially indicate wildfires associated with the immediate aftermath of impact, at least in local to regional areas around which the impact would have taken place. Other than this evidence, the Younger Dryas Impact Hypothesis is relatively convenient, as it explains three things that went on during this time. One, like we talked about, the Younger Dryas cooling, so the climate change itself. Two, the disappearance of the Clovis culture, or Clovis people, which are marked by specific tool making skills and stuff in the rock record. And we see at this time their disappearance in some sections, but I'll talk about some caveats associated with that later in the video. And then three, the extinctions of megafauna. Most of the megafauna, like woolly mammoths, the dire wolves, giant ground sloths, mastodons, giant armadillos or glyptodons, and giant short-faced bears, we see all of these types of megafauna going extinct by the end of the Younger Dryas, but kind of throughout that whole time frame. However, confirming major events in Earth's history, like impacts that caused global climate change and mass extinctions, requires major and global separate lines of evidence that corroborate each other. In other words, we need to see proxies, or chemical and physical indicators, in rocks that are located around the globe that all indicate the same event at the same time. This is exactly what we see with the KPG impact, or the Cretaceous Paleogene impact, that happened 66 million years ago. We have a crater. We have data surrounding this crater that shows, one, things like an iridium layer that thins as you get further away from the crater, the source of the iridium. You also see sinkholes and other things associated with impact, and shocked quartz, and all of these other impact indicators that I won't get into now, but we see these things around the impact site that indicates that this impact took place at this time. And then we also see, for millions of years after the impact, the indicators in the rock record that show how climate changed as a result of this massive impact, and obviously with the mass extinctions, which is another indicator. So we have all these proxies for things like the KPG impact. However, we don't really have all these things, all these proxies that line up with one another for the Younger Dryas impact. We have a lot of those proxies or indicators in the rock record, like I talked about earlier. We have iridium, we have nanodiamonds, we have microspherules or melt glass or whatever, but a lot of them have contradictory ages, and the dates just don't align with one another. And for a single impact event, you kind of need them to align. Some are even dated to after the megafauna extinctions, and so this wouldn't really make sense, because if it was the cause for, or a cause for, these extinctions, the impact proxies should show up in the rock record before the extinctions. And also, these proxies, like nanodiamonds, microspherules, and black mats, can also form by some high pressure, high temperature terrestrial processes, and don't necessarily necessitate an impact. And those that do indicate an impact cannot confirm that the impact was large enough to cause this kind of change. Many people have pointed out that there are impacts, extraterrestrial impacts to Earth all the time on a relatively small scale, and very rarely are they large enough to cause global mass extinction events and global climate change like at the KPG boundary. So maybe what we're seeing on a local scale in terms of impact proxies are just indicators of smaller impacts that didn't necessarily cause or contribute to the extinctions and the climate change, etc. But what about the disappearance of the Clovis people? Originally, it was thought that the Clovis people or Clovis culture of people disappeared at this time. And the question was whether an impact caused this or other factors. More recent research, however, shows that there was not necessarily a global abrupt disappearance of this culture. Rather, only local assemblages show their termination. And these terminations in specific units of the rock record suggest that they either just moved, as they were hunter-gatherer communities that moved a lot, and in some cases there's a direct transition from the Clovis culture to the Folsom culture, which suggests more so a cultural transition rather than extinction or disappearance. Moreover, many of these assemblages or rock sections that show these disappearances have ages that contradict the YDIH. That is, the rock record shows that in many of the sections or regions, the Clovis people lasted much longer after the proposed impact than they likely would have had the impact been a cause for their disappearance. But what about the extinction of the megafauna? One major problem with correlating the megafauna extinction with an impact is the spatial and temporal variation of these extinctions. Impacts tend to cause very rapid and temporally specific events, whereas these extinctions were relatively drawn out, locally isolated, and species specific. Thus, an impact doesn't really match what would typically cause that kind of extinction event. Maybe multiple globally distributed impacts that were spatially and temporally protracted, like the extinctions, might have contributed or caused these types of extinctions, but the YDIH proposes one major impactor at the Younger Dryas boundary 12.9 thousand years ago. And for context, this map on the bottom left here shows the timing of large animal extinctions on different continents. And we can see that this Younger Dryas timing of 10 to 12,000 years ago, most of the megafauna going extinct were in the Americas, which also correlates with the timing of human arrival to the Americas. And so it's more likely that human overhunting, as well as a mixture of that and the climate change that was going on during the Younger Dryas, both contributed to these megafauna extinctions, not necessarily a singular impact event, which would have caused global mass extinctions of the megafauna at the same time. It's also expected that an impact large enough to cause mass extinctions and global climate change would leave a crater, but none have been found. I think there was a crater found not long ago in Greenland that people thought originally might have represented the Younger Dryas impact. However, it was then later dated to, I think, over 50 million years old, so way before 12,000 years ago. And yes, it's true that impact craters and other geologic features can be relatively easily erased over geologic time, but there's also a lack of impact proxies that rule out a terrestrial cause for the Younger Dryas climate change. So that's one thing that should be noted. Yes, craters can be erased. However, young craters, like 12,000 year ago craters, probably shouldn't be erased by now. If we have the KPG crater from 66 million years ago, why don't we have this 12,000-year-old crater? There have been people that said, oh, maybe it hit ice and that didn't deeply impact Earth enough to save the crater impact site. There are a lot of hypotheses about this, but even without a crater, like, we just don't have enough other proxy data to really show that there was an impact of a magnitude that could cause these things. That said, if we didn't have any idea what caused the Younger Dryas cooling, the Younger Dryas Impact Hypothesis would probably gain more traction and warrant more attention, because we kind of need it, or need to invoke some extraterrestrial thing to explain this climate change, this rapid shift in climate trend during the Younger Dryas, But the problem here is we don't need it. We see other things that probably are more likely the causes of the Younger Dryas cooling. For example, massive volcanism and, most significantly probably, major and rapid changes to ocean circulation. What changed in the ocean circulation? Well, nearly a full shutdown of the ocean conveyor belt, or the major ocean circulation belt. Essentially, there's this thing called the Atlantic Meridional Overturning Circulation, which we shorthand called AMOC, and this part of the global ocean conveyor belt brings warm water from the equator north and vice versa, brings cold water from the Arctic south. And this entire conveyor belt is driven mainly by salinity and temperature. So essentially warmer, fresher water at the surface, shown by this red belt here at the surface, loses warmth through evaporation as it goes north, and at the same time it loses freshness as it becomes more saline due to the evaporation and the cooling, and then it sinks down into the deeper waters as it gets really cold, saline, and dense. And then this denser, cold, saline water moves south, becomes warmer, until eventually it comes back up through a process called upwelling. And this whole global conveyor belt is driven by mainly temperature and salinity, because these things control the water's density. So essentially, warmer, fresher water is at the surface. Sorry, my cat wanted to be in the video, I guess. And deeper, colder, saline water stays in the deep, the blue belt here, because colder, more saline water is denser. You want to be held during the video. I see. Okay. So, as the warm water from the equator moves north, it loses heat through evaporation, it loses freshness through evaporation, becomes colder, more saline, until it gets to the north. It sinks into the cold, saline, dense, deep water current, and this overturning happens that drives the conveyor belt forward. But it's thought that at this time, just before the Younger Dryas, an influx of fresh water into the northern Atlantic from melting ice weakened the AMOC, and this caused rapid cooling in certain regions, which was intensified by positive feedback mechanisms. So what caused this huge influx of fresh water to the northern Atlantic? Well, there was this massive Lake Agassiz, or, well, at the time, what was a glacial ice sheet over kind of nearly all of Canada, or at least kind of northeastern Canada regions, that began to melt just before the Younger Dryas. Why? Well, let's recall the rapid warming that happened just before the Younger Dryas. This beginning of the interglacial that we're now in, after the last glacial maximum, marked this rise in temperature that led to massive melting of this glacier. And remember, glaciers, ice, they're fresh water, and all of this starts to melt and leads to all this fresh water going into the Atlantic Ocean. And remember, temperature and salinity differences drive the ocean conveyor belt. And when this region where the AMOC turns over that current got flooded by all this fresh water, it weakened those salinity differences enough to essentially shut down the AMOC to the point that a rapid cooling occurred, because that warm equatorial water wasn't being brought to the north. But wait, there have been a lot of reports recently suggesting that the AMOC could collapse in our near future due to modern warming and the influx of fresh water into the North Atlantic and Arctic. So does this mean that if the AMOC collapses in our near future, it would cause cooling like the Younger Dryas? And wouldn't this help our current global warming scenario? Well, not necessarily. Combined with greenhouse warming, which was not necessarily a factor when it came to the Younger Dryas, this event could worsen warming and melting in certain regions of the globe, which in our current climate scenario is probably going to take over climate feedbacks more so than a slight northern hemisphere cooling that would result from this AMOC collapse. So in other words, what's more than likely is an AMOC collapse would lead to heat not getting transferred north as strongly and therefore staying more south. And globally, this would mean a lot more melting in the southern hemisphere, which would again cause more rapid melting globally, because that leads to an albedo positive feedback mechanism in which less ice leads to more solar radiation absorption by Earth's surfaces. That said, the AMOC collapse could also lead to slightly cooler conditions and weirder or different weather patterns in the northern hemisphere, especially in Europe and the regions that are directly affected by the lack of transfer of warm equatorial waters up to the north. So this could mean cooler conditions in those regions. But that said, we call it climate change for a reason. We're not just trying to fight warming. Rapid warming and rapid cooling can be detrimental, as we see with the Younger Dryas having caused mass extinctions. In any case, I also want to point out that the AMOC doesn't just transfer heat, it also transfers carbon and other nutrients. Therefore, a collapse of this part of the ocean circulation belt would also greatly affect life and ecosystems, probably not in the best of ways if it's preventing transfer and mixing of nutrients. In any case, back to the topic at hand in terms of this video, to summarize the Younger Dryas cooling and what caused it, more data should probably be collected before we completely rule out the impact hypothesis. That said, even if there was an impact that contributed to the climate change and potentially the mass extinctions, there were a lot of other factors that also probably at the same time contributed to causing these things. If you want to hear more about how human overhunting and other human activities affected the megafauna and led to some of their extinctions or at least restriction, I talk more about that in the recent video I made about the megafauna and their extinction, so I will link that somewhere on the screen for you. And with that, thank you so much for watching, and I'll see you guys next time. Bye.